So the motor effect is basically the force that occurs when two magnetic fields are overlapping. And we talked about it in terms of a simple electric motor, all right? So this is the motion caused by two overlapping magnetic fields. So the idea is that if you have a permanent magnet here, okay, so you have north and south pole, right? You're going to have your magnetic field between these two will look like this. It's a uniform one, so the lines should be straight and evenly spaced to the eye, arrows going from north to south, all right? So that's one magnetic field, all right? Then if I have, let's say, a wire that is passing, that is being put through that magnetic field, all right? So this is my, oops. This is my wire, okay? And it's coming out of the page here, as evidenced by my little dot. All right. So according to the right-hand rule, right, if it's coming out of the page, this is the current coming out, the magnetic field is going to curve around this way. So it's going to be going in this direction. So my magnetic field, let me draw that. Sorry, this is not drawn very well, but your arrows should be going here and here. They'll be going up. Okay, let's pretend that, yeah, that's beautiful. Okay. And so the idea is that these are two overlapping magnetic fields, yes? And the motion is caused because, as you can see here at the bottom, these arrows are going in the same direction. I'm trying to do enough pictures to get more colors here. Okay, so these arrows are going in the same direction, yes? Which means that, and here they're going in the opposite direction. Now the permanent magnetic field is going to the right, and the one caused by the current in the wire is going to the left. So these magnetic fields are going to cancel each other out to some degree, whereas here they are reinforcing each other. They're both going in the same direction. So what happens is the force, the overlapping ones cause a greater force than up here, and so the wire is going to be pushed up and out of the magnetic field here. So this is the force, the direction of the force that is being experienced, all right? And so you should be able to reason through this and also talk about it, all right? The idea that two overlapping magnetic fields causes a force on a wire, and that causes and hence causing the motion, all right? Now, but you should also be able to always talk about which way these directions are going. So rather than having to draw this every time, you do the left-hand rule. Okay, so this is my left hand. And the idea is that you have your fingers, they're all at right angles to each other. See that? It's a three-dimensional, right? Right angle. So this one's going out to the side, this one's going directly forward, and this one's going directly up at the camera, at you guys. Okay. And so these are the three fingers. Now, the first finger is the magnetic field, FF, first field. All right, so this is the magnetic field. So for example, here, okay, I have the magnetic field going from north to south, okay? The second finger is the current, second with a C, current, it's stretching, but still second is the current. The current here is going up out of the page. So I turn my hand, ouch, very carefully like this. So I have my magnetic field going this way, the current's coming this way. And so that means that my thumb represents, you can think of it as the motion, thumb motion, MM, all right? And so the motion of the wire, the force on the wire is going to be acting up, and that's exactly what I've drawn here. So that's the idea. This is called the left-hand rule, and you need to remember what each one stands for. So let's write that down. The left-hand rule, sometimes called, I'm going to abbreviate it LHR. The thumb is the motion or the force, the direction of the force. MM. Okay. The first finger is the magnetic field. FF, first field. And the second finger is the direction of the current, C and C. Oops. So that's your left-hand rule, and that's how you can tell what the direction of that force and that motion. All right. Now, the way that this, and so the way that we use this, or the way that you guys need to understand we use it, is in an electric motor. All right. And again, rather than spending even more paper printing things out, I just using the book here, wait for that to adjust. There we go. So this is an electric motor, right? And so the idea is that you have here the arrows showing you the current. Remember that current always flows from positive to negative, and the long end of the battery or the cell is the positive. So it's going from positive through here into the negative. All right. And so the idea is that here on the left side where the current is going down, it's going to experience a force moving up, right? So if I have my magnetic field is here, right? The current, yeah, is going down, right? This is on this side of the, can everybody see that? Yeah, on this side here. Okay, the current is coming downward, so this is my second, and the force then is going up. So this is being forced up, and then on the other side, it's the other way around, which I can't, it's a little difficult to get my hand down that way, and you can't see it. And so the force is going down. And so the idea is that this makes, because there's a force upwards on one side and downwards on one side, it makes it spin. And that spinning works as long as the current is always going in the same direction within that magnetic field. So that's the purpose of the split ring commutator, is that you can see there's little spaces in it, right? So the wire is spinning, and when it gets exactly vertical, that's when the connections with the brushes, which are actually the one actually connecting it to the battery, completing the circuit, are broken, but it's already moving. So the momentum keeps it going. And then the split ring commutator here in the middle will again make contact with those brushes after these spaces have been passed, and you'll get the current continuing to flow up on the right side and down on the left side always. And that's what the split ring commutator allows. The carbon brushes are just the contacts for that brush to complete the circuit. And so that's a simple electric motor. All right. You do have, it's a direct current motor, right? Obviously, if this were an alternating current, that wouldn't work very well. So the idea is that you have, it's a direct current, and it's what it's called, a simple electric motor, a DC electric motor. If you want this to spin faster, there's 3 ways you can do that. You can increase the number of turns or loops of wire, right? So you can have this coiled several times, and any electric motor you actually look at will have many, many coils, obviously. You can increase the strength of the permanent magnetic field, or you can increase the current in the wire, and that will make it spin faster because there's a stronger current, which means that there's a stronger interaction between the 2 magnetic fields. All right. So that's a simple DC electric motor, and the motor effect summarizes the this is the first part of electromagnetism that people were asking about.